In a previous attempt to find a solution to the representation of primes as x squared plus minus n times y squared, we rediscovered Gauss formulas. This was initially a hunch aimed at extending the simpler known cases, but the generalization to the first primes might be novel. We first show how Gauss formulas apply to representation of primes, and later we show how they may be derived with elementary tools and not complex multiplication as done by Hans Riesel and Richard Brent. Using them to find a representation of primes is surely an overkill for a bigger n, but a nice solution for small ones. Let's initially explore the functionality of Gauss cyclotomic formulas across various primes forms. We'll start with primes 6k plus 1. According to Fermat's little theorem, when A and P are coprime and P is a prime number, then P divides A raised to P minus 1 minus 1. For primes of the form 6k plus 1, this theorem implies that A raised to 6k minus 1 can be factored into two brackets, with P dividing one of them. Upon computational examination, it becomes evident that P divides the first bracket for about 1/3 of all values, while it divides the second bracket for about 2/3. This is Gauss cyclotomic formula for power 3. So if P divides the second bracket of Fermat's little theorem algebraic form, then it also divides Gauss cyclotomic formula for power 3. Let's illustrate with two examples related to the form 6k plus 1. The first one is prime 73. Upon examination, we check that for A equals 2, 73 divides A raised to 4 times 12 plus A raised to 2 times 12 plus 1. We can scale down the values involved by finding out the residue of 2 raised to 2 times 12 modulo 73, which is 8. Substituting this in Gauss cyclotomic formula, we arrive at 7 squared plus 3 times 9 squared equals 73 times 4. Employing the simple descent, we compute that the residues of 7 and 9 modulo 4, yielding minus 1 and 1 respectively. Consequently, 1 squared plus 3 times 1 squared equals 4. Finally, applying extended Brahmagupta's identity yields that 73 times 4 squared equals 20 squared plus 3 times 16 squared. As both squares are divisible by 4, once divided, we get the desired solution. 73 equals 5 squared plus 3 times 4 squared. The second example is prime 547. The method is just the same, yielding that 547 equals 20 squared plus 3 times 7 squared. Primes of the form 10k plus 1 divide Gauss cyclotomic formula for power 5 in 4/5 of A values, that is between 0 and P minus 1. So we can illustrate how it applies for finding a representation as x squared minus 5 times y squared for primes 131 and 521. Note that we can also derive 521's representation as x squared plus 5 times y squared with the help of an auxiliary congruence, as 3 is a quadratic non-residue of 521. Now it's time to examine primes of the form 14k plus 1, which divide Gauss cyclotomic formula for power 7 in 6/7 of A values between 0 and P minus 1. Below, two examples, primes 449 and 1583, and how we applied the method for finding a representation as x squared plus 7 times y squared. Finally, we can illustrate how the method applies for primes of the form 22k plus 1. Here are the calculations for prime 2113. Press pause if needed. And here are the calculations for prime 1871, where we cannot find a representation as desired. It is interesting to notice that 20 can be represented as x squared plus 11 times y squared as shown below. However, this representation doesn't imply that the square of 20 would divide both squares in the extended Brahma-Gupta's identity. To clarify, if we were to assume this, it would imply that 1871 could also be represented as x squared plus 11 times y squared. However, upon numerical verification, this isn't the case. Indeed, by combining the equations displayed in light blue and gray colors, we can discern that both 3 times 4 and 3 times 25 can be represented as x squared plus 11 times y squared. That is, setting 1871 aside, we do find those representations. But neither 3 nor 4 nor 1871 have their own representation as x squared plus 11 times y squared. Having examined the functionality of Gauss cyclotomic formulas across various prime forms, let's now delve into their application specifically for a chosen prime. We chose 547 as we can try finding representation where n is 3, 7, or minus 13. Thanks to Fermat's little theorem, when examined it with algebraic lenses, we are sure that 547 do divide x squared plus n times y squared for these values of n. Here we can see how those cyclotomic formulas apply for each possible combination of 3, 7, and 13. And at the right side, we illustrate how we can calculate the number of values of A in the range 0 to 147 minus 1, where 547 divide the cyclotomic formula. Notice that we can also find cases where 547 divide the cyclotomic formula when n equals 3 times 7, 3 times 13, 7 times 13, and 3 times 7 times 13. However, it's important to observe that the numbers of values of A that satisfy this divisibility condition significantly decreases in each case. Finally, we illustrate how 547 can be represented as x squared plus 3 times y squared, represented as x squared plus 7 times y squared, and x squared minus 13 times y squared. So far, we've been using Gauss cyclotomic formulas to determine representation of primes in the form x squared plus minus n times y squared. Yet, the question arises, how can we derive these formulas, particularly the coefficients of the homogeneous polynomials, using elementary tools? In Hans Riesel's book, Prime Numbers and Computer Methods for Factorization, Riesel and Richard Brent present a method to derive them, albeit relying on complex multiplication rather than elementary techniques. Below, a table showcasing the coefficients of the homogeneous polynomials x and y. Actually, the coefficients of polynomial x matches with the formula we present here, where n sub k is a quotient and r sub k is the residue of the congruence of 2 times p minus 1 over 2 combination k modulo p. In fact, the coefficients of polynomial x are r sub k, that is, n sub k equals 0, for all primes smaller than 41. Let's see the first few cases for primes 3, 5, 7, 11, 13, 17. But for primes bigger than 41, n sub k is bigger than 1. Let's illustrate how the formula works for prime 61. Let's do a recap. We first explored Fermat's little theorem through algebraic lenses, seeing how Gauss cyclotomic formulas apply in the representation of primes as x squared plus minus n times y squared. Then, we showed how Gauss cyclotomic formulas may be derived with elementary tools, and not complex multiplication as done by Hans Riesel and Richard Brent. Interestingly, while determining R sub k is rather straightforward, calculating x sub k poses challenges due to the need of finding the correct plus-minus sign and the value of quotient n sub k. This quotient may be 0 for all k coefficients when the prime is small, but tends to be different from 0 as primes become larger. It's clear that using this method to compute Gauss cyclotomic formulas for the purpose of finding a representation x squared plus minus n times y squared for any prime, whether large or small, may be excessive for larger values of n, but it still proves to be a practical solution for smaller ones. In the next appendix, we'll derive multiple Gauss cyclotomic formulas as x squared minus n times y squared for primes 4k plus 1 using Lucas and Fibonacci polynomials.